So I would like to welcome everybody to the first of our TSC seminars this year. We're opening with an exciting topic of carbon capture, and I would like to introduce Professor Faruque Hasan, who is Associate Professor of Chemical Engineering at Texas A&M University. He is also Assistant Director of the Texas A&M Energy Institute, where he is Director of Decarbonization, which is a topic, and carbon capture is definitely a topic of growing interest at Mitsubishi Electric and at MERL. And so we are very much looking forward to hearing what you have to teach us today, Faruque. And so I'll turn it over to you. And as always, if people have questions, it would be best to hold them to the end. If there's a question you want to ask to clarify, send a note or put your hand up. Thank you. Faruque.
Thank you. Good afternoon, everyone. And first of all, I'd like to thank Scott and Arvid and everyone for joining, and also for the kind invitation. I'm really excited to talk about some of the things that we have been doing in the area of carbon capture. Can you guys see my screen?
Yes, it looks great.
Great. Okay. All right. So I'm just thinking like what I should really, capture here in this talk. And then I just thought that maybe I will start with giving an overview of the carbon capture, utilization, and storage, or CCUS. Many of you know that this is an important area that people have been talking about lately. A lot of interest in this area. And then I'll talk about some of the work that we did because of the key issues that we found in terms of systems engineering in this area. And then some of the remaining challenges before I conclude. I am a process systems engineer by training, and the work that we do in our group at Texas A&M mainly focuses on the systems aspects of energy and decarbonization. So overall, the theme would be in this talk, systems-wide thinking. And I'll try to argue that this is something is important, even addressing societal challenges and I know some of the technical challenges that we see in terms of carbon capture. So systems-wide thinking and structure at different scales is one of the key aspects that I want to highlight. Just briefly going back to why we're interested in carbon capture, everybody knows that CO2 emission is a global challenge, and we see this famous plot where we are now able to see the increase in atmospheric concentration of CO2 over many years. If you put it in the context of larger time, you see that there is a significant rise in these concentrations. About I guess 10 years ago, we surpassed the 400 ppm level in the atmosphere concentration, and CO2 being a greenhouse gas, it kind of puts us in a very challenging situation of global warming. And now it's a consensus that CO2 contributes to the global warming. And there are different scenarios I'm showing in the right-hand side here on the slide that depending on how we continue emitting carbon dioxide to the atmosphere or reduce its emission, we'll end up with different types of global warming scenarios. Even in the case where we have drastic measures to reduce the CO2 emission, still with policies and pledges, it will take some time to bring the CO2 back to the level where we want. And the target currently is about 1.5 degree to 2 degrees centigrade of the temperature that we want to keep in from the pre-industrial level. Now, if we already have discussed and seen that CO2 emission, and due to that, the global warming and climate change are happening. There are different adverse effects all over the world. There are intensity in storms, droughts, and others. So this is a global issue. So what can we do about reducing the CO2 emissions? So that's where carbon capture, utilization, storage comes in. The bigger picture here is that there are a lot of stationary sources of CO2 emissions, like power generation, those power plants based on coal, natural gas, or even petroleum. There are chemical industries, petroleum industries, there are cement industry, iron and steel, and others. These are large sources of CO2. So the idea here is that if we have a technology that can separate that carbon dioxide from the flue gas, then we can transport it and either store underground or utilize for other purposes like enhanced oil recovery or even converting CO2 to some value-added chemicals. So this is the overall idea of carbon capture, utilization, and storage. Now, when I say capture, this is a chemical process that I'm referring to mostly. When we mix something that is spontaneous, right, it happens spontaneously. But if I want to separate, especially a mixture of gases like carbon dioxide, nitrogen, these are the two predominant gases that we find when we have a CO2 emission source. This separation is not easy. We're all working against the thermodynamics, right? So we have to put a lot of energy, we have to invest. So cost and energy penalty, these are the two major issues in carbon capture. And then for utilization, there exist technologies there where we can use the captured CO2, for example, for enhanced oil recovery. But the argument there again goes against is using petroleum, because we may not want to use that for getting more carbon out of the ground. When I talk about storage, it's primarily the long-term isolation and sequestration of CO2 that we capture, either in underground, storage. We have many reservoirs like saline formations underground, brine solutions, where you can dissolve CO2 and keep it for long term. Now, there are some technical challenges when we talk about capture. The capture has some requirement. For example, if I have a source, typically it is dilute in carbon dioxide. So when I want to concentrate by separating it, I have a target of separation. For example, if I have a source with 15% carbon dioxide, the target is to make it 95% pure. Why? Because otherwise we'll need to deal with a significant volume of gas, which is mostly nitrogen, and it doesn't have any use. So purity is important. And then we want to have a target capture. The Department of Energy, typically when they talk about post-combustion carbon capture, they have a target of capturing 90% of the CO2 that is present in the source. If I take this 95% or 90% purity and recovery, then the capture becomes challenging technological problem. Once we capture that, to transport that CO2, we again need to compress it at very high pressure, typically pipeline pressure more than 100 or 150 bar. And also it is useful to make it super critical CO2 for sequestration purposes, which again needs high pressure compression. All right, now interesting fact about CCUS is that, again, as I mentioned, that we have different sources of CO2, then we have chemical process that is employed to capture or separate that CO2 from other gases, predominantly nitrogen. Then we transport and for utilization or storage purposes. If you look into the CO2 value chain, it is very interesting that it is kind of in the opposite direction of the petroleum energy value chain. What is upstream for CO2 is actually the downstream for the energy or process heating based on petroleum, and then what is upstream for CO2 is actually downstream for the energy and vice versa. So there are many technologies which already exist in terms of in this CCUS domain, but there are a lot of challenges that also remain. Now, why CCUS? Well, I mean, CCUS is not the ultimate solution for the green and renewable energy. Well, as we make this transition from fossil fuel based to renewables, we need some time, and we also need to accelerate the rate of decarbonization, and it's not easy. We need to bring down the cost and availability of our renewables. Renewables has intermittency and uncertainty in themselves, and then technology needs to scale. So while we address all these challenges, to have time, we need technologies like CCUS. Also, there are there are places where we may not be able to implement renewable energy immediately. So again, for existing fleet of chemical industry, power industry, if we want to reduce carbon emission, then maybe CCUS is a bridging or a technology that we can employ. But by no means it is not the only technology for decarbonization. Well, there are many other ways. For example, we can switch fuel. We can switch from coal to natural gas, from natural gas to a mix of hydrogen and natural gas. That will increase our decarbonization pathways. We can increase the efficiency of our technologies. We can make a mix of energy that is diverse, including renewables, nuclear, geothermal, solar, wind. So all these can reduce CO2 emission, but where CCUS comes is again, as I said, as a bridging technology between what we have now versus where we want to go in future of sustainable energy transition. There are other economic drivers, also policy drivers that make CCUS very interesting at the present time. Tax credit incentives, for example, like 45Q, where if you capture carbon dioxide and sequester in underground saline formations, you can actually claim tax credit. If you invest in renewable energy or energy transition, you can also claim credit for that. If you bring green hydrogen and along with, let's say, carbon capture, you can also have incentive for those. So all these make these current dynamics for carbon capture, utilization, storage very interesting. And so now we want to answer what kind of capture we should think about, where we should do those capture, where we should utilize and sequester. So those becomes very interesting systems engineering problems. And there exist, many different places where across the world there are, pilot plants, there are demonstration plants that are currently working on CCUS demonstration to answer different, questions regarding uncertainties, the cost, what will be the scale, what will be the supply chain. All these questions are coming up. So that's where I think systems engineering can contribute a lot in this domain. Now, in this supply chain of carbon capture, utilization, storage, the major piece is the capture part, because 2/3 or even more of the cost and the energy that goes into the supply chain of CCUS belongs to carbon capture. So that is very important part of it. And as I mentioned, it is kind of a chemical process where you are taking a mixture of gases and then separates the CO2. And CO2 is the less, predominant gas in that mixture. So it is very dilute. So we need to have some sort of either chemical or physical separation. And most popular separation is called absorption-based capture, as you all know. And monoethanol amine is the chemical that is most popular in this domain, but there exist other amines and other solvents. Essentially, the idea here is that you bring a solvent which selectively dissolves and absorbs carbon dioxide from the mixture of gases, and then you use a regeneration technique, either put heat or reduce the pressure to dissolve that captured CO2. So you need some kind of absorption and desorption going on together within a closed loop of solvent regeneration that gives you the entire process. One of the schematic that I'm showing in the in the bottom corner here. So the idea here is that you capture CO2 in the absorber and let the clean gas go out. Without that purified gas doesn't have CO2, but the solution that you're using as a solvent captures CO2, it becomes rich. You pump it and put it in a desorber, and you put a lot of heat there in the reboiler that increases the temperature, which kind of moves the equilibrium of the absorbed CO2, and it dissolves from the solution, and you get a product CO2. As you can see that there is a significant demand for energy in the reboiler and many other cases where, for example, if you want to compress the CO2 to 150 bar for pipeline transportation, so you need to have energy there too. Now you can have there are significant opportunities if you take this simple process flow sheet and then try to integrate energy between capture and compression. That's what we did several years ago when we started working in this area, that we looked into these process configurations and then apply heat integration and optimization techniques to improve the energy integration and overall energy demand of this process. And here one example I'm showing that we could actually improve the process by 30% in terms of the energy efficiency. So there are a lot of opportunities for optimization there, that how can you improve the capture process. There are a lot of opportunities also in terms of selection of materials. For example, you can change MEA to other materials and do the optimization at the process scale and see how much energy it needs. So that's kind of the absorption technology. Then you can also use adsorbent, where the idea is that the phenomena is now not at the solution but at the surface of solid adsorbent. There exist many microporous materials which selectively adsorb carbon dioxide. For example, zeolites, metal organic frameworks, porous polymer networks, and there are many materials of this class are coming out almost every day that has very high surface area and internal volume, which can be used to selectively capture CO2 using adsorption technique. And adsorption in general is also used in chemical processing, for example, like separation of natural gas. But in the domain of carbon capture, it is relatively new. It is not as popular as the previous solvent-based absorption technology, but it is an upcoming technology. The idea here again is that you can exploit the partial pressure and the equilibrium conditions for the adsorption and desorption. So if you have high pressure, CO2 will be absorbed more, and then if you reduce the pressure, then it will dissolve based on the equilibrium. You can also change that equilibrium by changing the temperature. You can adsorb at lower temperature and then dissolve at higher temperature, and you can combine even this pressure and temperature, both degrees of freedom, or you can apply these driving forces in a combined manner. But the challenge is again is that to do these changes or swing, where we call this pressure swing or temperature swing adsorption techniques, you need to provide a lot of energy. For example, to dissolve the carbon dioxide, which is very selectively adsorbed, you need to put a lot of energy for creating vacuum. You need to go significantly low pressure to dissolve that CO2, and vacuum pumps are very energy intensive. Same thing if you want to dissolve CO2 using temperature, so you need to have a higher temperature, so you need to provide a lot of process heating there. one example that we worked on this domain of carbon capture is again we several years ago we designed this process. Now we have a patent on this, which is a multi-step, periodic and dynamic process for capturing CO2. The idea is that you pack a column of these materials using these materials like zeolites, and then you pass the gas, which is a mixture of carbon dioxide and nitrogen, which you call flue gas. The idea is that we want to selectively absorb CO2, but you need multiple steps to be able to achieve the required purity and recovery that I mentioned earlier, the targets that is set for carbon capture. So to do that, you have to operate this column in a dynamic fashion, in a periodic fashion. In this particular design, we have 4 steps. So in the first step, we increase the pressure of the column by closing the valves on the top, but opening the valve on the bottom and pushing the gas inside the column. So the mixture of carbon dioxide and nitrogen go inside, but the zeolite selectively absorb only carbon dioxide. And so in the next step, you continue pushing the gas, but opens up the other side. So since the nitrogen is not absorbed, it will come out because of the driving force that we have. Now, so you keep pushing this step, pushing the gas for some time, but you cannot do it for long because at some point this whole bed will be, or the column will be saturated with absorbed CO2. After that, you will not absorb anymore. So you will lose CO2 from the top side of the column again. So you don't want to do that. So you stop this step for some time, after some time, and then create vacuum from one side that I'm showing. The idea here is that you just create a little bit of vacuum, which we call the blowdown step. In this case, you want to remove the rest of the nitrogen that are within the column to increase the purity of the final CO2 or carbon dioxide product. So you run that step for some time, and then finally you stop it, and then reduce the pressure even further, but open up the other side, where then you get the most of the carbon dioxide out from the process at very low pressure. So these 4 steps are operated in a cyclic or periodic manner. So once you complete the first step, you go back again the first step and continue doing it. So it is not a steady state process. It is a dynamic and periodic process. But you need to be very careful to design it optimally and operate in a very optimal fashion, because otherwise you may end up with very high energy consumption or very high cost of separation. Depending on the operating conditions and design of this column, you will end up with different performance. So optimization is very important for these, and that's what we did. But optimization is also challenging. Here I'm trying to optimize the length of the column, optimize the different pressure level that I should operate for pressurization, absorption, and evacuation, and how long each of these steps should be run. So this is a very challenging problem. On top of the dynamics that we have of the absorption is very non-linear. So eventually it ends up kind of very complex model, but I'm not going to describe this entirely. It's a busy slide, but what we are essentially proposing here is that we use mass and energy conservation laws and your operational constraints as a model, and then that represents this entire system that operates in a 4-step manner, and then try to use this simulation platform to come up with optimal design. Because it's a very nonlinear partial differential equation-based model, challenging optimization part is very challenging. So for that, we kind of devised a different approach for optimization, which we call constrained graybox optimization, where some of the constraints in the optimization are known. That, for example, we know how it is the level of purity we want, what is the recovery we want, but we also don't know how this entire process is working in the very dynamic over time and space, which is represented by the dynamic model that I showed earlier. So we use that, we treat that simulation model as a black box. So combining these two, we end up with a gray box model, of which we use a trust region-based optimization technique to optimize and finally come up with the design. And we are very successful in coming up with a new design, which eventually ended up with low cost and low energy consumption process, which we currently have a patent now on that. Very interesting result on that. Okay. Lastly, I want to also talk about another capture technology that most recent development that happened in our group in collaboration with my colleague at Texas A&M. This is a new type of technology which we call Cryol. Cryol stands for cryogenic liquefaction technique. So here, instead of using absorption or adsorption, we are kind of compressing and cooling in a sequential manner the entire mixture of the gas, and then try at a lower pressure, lower temperature and high pressure, we kind of achieve phase separation. So CO2 is kind of separated based on that separation that happens at a low temperature and high pressure using refrigeration cycles. And this is not a new idea, but previously many people thought that this is very energy intensive and costly because we are putting a lot of energy for compression. But again, with the background that we have in terms of optimization and process design and intensification, we are able to systematically come up with a very novel design in terms of multiple refrigeration cycles and how they can be integrated, which leads to a much lower cost. I'm showing in this right-hand side plot where Cryol, this technology stands in terms of the cost of capture and compression of CO2. This plot is very interesting. Here is that in the x-axis it shows the flue gas composition, which kind of represents the source. If you have a coal-fired power plant, for example, then the composition is about 15%. If you have an engine that burns fossil fuel like natural gas, and it produces a flue gas, it has about 5% or even less CO2. So then the scale would be here. And on the vertical scale, I'm showing the cost of different technologies that you may think. As I mentioned earlier, it could be absorption-based technology like using solvent like MEA, or it could be a membrane, it could be a pressure swing or temperature swing or vacuum swing absorption. So when you do this optimization on different technologies and calculate the optimal or minimum cost of capture and compression and put it here as a function of flue gas composition, you see a very interesting result is that as you have higher composition of the feedstock CO2, then you have less cost. But most of our sources of carbon or CO2 is very dilute, so it will be ranging between 4 to let's say 15%. So in that range, we are talking about more than $50 per ton of CO2 capture, which is very high. But unlike many other technologies, the Cryol can capture CO2 about $25 or so. So that made us very excited about these, and eventually we actually started a spin-off company last year from Texas A&M on Cryol. There are a lot of interest. We're talking to a couple of industries in the Houston area who can take these and for commercialization aspect of these. So to summarize, on capture, there exist different technologies, as I mentioned, like absorption, adsorption, cryogenic. I did not mention about membrane, but membrane is also upcoming technology of membrane separation can be used. In each of these process or technologies, you need to have another layer of decision that what kind of material you should use. As I mentioned about zeolites, and I will talk about it a bit more on zeolite, that there exist many choices for zeolites. So the question there becomes, okay, what is the optimal zeolite, and what is the best process around that zeolite that you can design to capture CO2? And again, the goal is to reduce the cost.
Hasan, can I just maybe interrupt for a second? So we have a question from Hasan.
Absolutely. Yeah.
So,
Scott, I thought you were talking to me initially.
yeah, I'm sorry. Names
Hi,
confuse
Faruque.
me sometimes.
Hi.
I had a quick question, and I've seen this a lot. So a lot of times we see the metric being the cost in dollars per ton of CO2 captured. When we talk about CO2 captured, are we talking about net CO2 captured, or does that I mean actually factor in the amount of CO2 that is actually emitted in order to produce the power or the energy needed to perform that capturing?
Yes, I mean, that's a great question. 2 points I want to highlight, and thanks for bringing this, is that there are a lot of confusion, exactly as you mentioned, in terms of when people mention, okay, what is the cost of CO2 capture? We need to be very cognizant about these, that there is cost of capture, which includes the investment cost and the operating cost and maintenance cost of the process. And that does not include the indirect CO2 emission that might happen if I'm using energy for capturing CO2, and that energy comes from another fossil fuel source, right? So that fossil fuel, again, will emit CO2. So in that case, we need to talk about cost of avoidance, right? Net CO2 avoidance, and that's very important. Yes. Yeah, so that avoidance cost is much higher, is higher typically than the capture cost, typically. Well, we also need to know what is the absolute cost of capture, because in future more and more renewable energy can be integrated to supply that energy, and that might not have a high indirect CO2 emission.
Thank you.
Thank you. The other point that I want to mention is that when again somebody says, okay, what is the cost of capture? We need to be also a bit cautious about the source of the CO2, right? If somebody says, okay, the cost of this technology is $50, that is not entirely a complete answer, because the cost can be 50 for, let's say, separating carbon dioxide from a flue gas, which is very concentrated in CO2. But if you reduce the CO2 concentration, if you go from coal-fired to, let's say, natural gas-fired, then it is much more costly for every ton of CO2 that you capture, because you're normalizing, your source is dilute and you have less amount of CO2 that you're capturing. So that cost per ton will go up. So this is another point that I want to bring in, that when we did this study in terms of cost as a function of composition, it has to be captured like that. Otherwise, we might end up with wrong decision. Okay, so just quickly moving on to the sequestration of the storage side. I'm not an expert in the storage per se. I have colleagues, for example, in the petroleum engineering department who are expert in this. But the idea is that once you capture the CO2, you can then store, in underground geological sequestration sites. There exist many saline aquifers, depleted oil and gas reservoirs, unminable coal beds, where you can push the CO2 at high pressure, and then the hope is that you have monitoring and characterization of those reservoirs done very carefully, so that you can store them for long-term sequestration. And we did some study on that. What if I ask this question, that I have many sources of CO2. If I take a country or a region, like here I'm taking, let's say taking the United States as a whole, and I'm just only considering the stationary sources of CO2. So the first figure that you saw on the top with those circles, each of these circles represents the large stationary sources of carbon dioxide. The color represents different types of composition that we have. The red, for example, is about 15% CO2 coming from coal-fired power plants. On the other hand, the green, blue, or cyan colors and smaller dots represent natural gas-fired power plants, which have less CO2 composition. So if you take all these different large sources, and then there exists data from Department of Energy and other sources that where we can actually sequester. For example, these green locations are actually underground saline formations where you can potentially store CO2. The blue here I'm showing in terms of different, CO2 potential locations for CO2's utilization in terms of natural gas reservoirs. And then the yellow ones are unminable coal beds where you can again put CO2 there. So if we have this kind of system-wide question that are given the sources, given the sinks of carbon dioxide, where should I capture, how much should I capture, which technology should I use, which material should I use to answer questions like, if I want to reduce the 50% or half of the total emission from these two sources, so what should be the minimum cost? A network that we should think of. What will be that cost? How much investment we need to provide? So that is a systems level question, and we can answer those again providing this kind of information in optimization strategy, and I'll talk about it very quickly in the last part of my talk. But there exists this kind of data and the supply chain configuration questions that you can address at CCUS level. It's not easy, just to give an example that if you want to consider that kind of system, the decision space is very large, but fortunately we can apply, optimization techniques like mixed integer linear programming or nonlinear programming to address those kind of questions. Okay, some of the challenges that I want to highlight in the capture space, given the different technology that I discussed. One of the challenges is high energy penalty, and the other one is when you have high energy penalty, means you need to put a lot of energy, you need to have a lot of investment also for the equipment, so the cost goes up. So here is a theoretical calculation that if you want to do, let's take a power plant. Typically, the scale that we're talking about of a power plant, let's say if you take a 500 megawatt power plant, it emits about almost like, if it is coal-fired, coal-based, then it emits about almost 10,000 tons of CO2 every day. It's a very large scale. So just to know how much energy we need to provide to capture that CO2, you can do these very simple thermodynamic calculations by considering, 100% reversible separation, which will not happen in reality, but will give us a minimum bound on the energy that we need to put. And you can take that as the negative of the Gibbs energy of mixing a difference in energy, then you do that calculation, and it turns out that for every kilogram of carbon dioxide that you want to separate, you need to provide about 0.17 or more megajoules of energy, which is very high. To put in the context of a power plant, this theoretically minimum energy correspond to about 4% of the overall power plant energy that it produces itself. But if you consider a realistic process for capturing that CO2, the energy consumption is much, much higher than that theoretical minimum. It's because of the loss in energy, the irreversibility, and all the inefficiency that we have currently in the process. So there exists a lot of opportunity in this domain to reduce the energy consumption. And again, putting that in the context of the cost, because at the end of the day, we're going to use this metric to decide which technology we're going to implement or deploy. So we need to do this study again for different composition of the CO2. All right. The other challenge, I already touched upon this, is that we have a diverse scenarios of sources. Here I'm listing of just the stationary sources like power plants, chemical industries, processing, agriculture processing, petroleum processing, iron and steel, and all these. If you look into this, their scales are different. Their compositions of CO2 that initially we have in the flue gas are much more different. So it's not easy to say that we should implement this technology versus that, or we should just go for one technology, because depending on what a condition, what place, what type of source you're talking about, the selection would be different. So that's a very big challenge in CCUS design. Here I'm showing some representative composition, again for across different technologies and different industries, and you can see that the composition can be as low as 4% and as high as almost 50%. And just remember that I'm not even talking about direct air capture. right? Capturing CO2 from air, which is entirely a different and most challenging separation problem, where the composition is about 0.004%, right, or 400 ppm. So depending, again, the message here is that we need to be very cognizant about this composition. And I know that a lot of interest in Mitsubishi and others that how do we decarbonize, let's say, transportation sector, right? And that is one of the most difficult to decarbonize if you even think about carbon capture, because the scale is very different. All the result that I'm showing is in the order of million tons of carbon dioxide captured per year, because that's the scale for power generation and electricity generation. But what if I want to capture CO2 from a train, or let's say from a diesel engine truck, right? So these are very different questions, and the cost and energy consumption and even the supply chain of that CO2 management is going to be very different. So these are unresolved question, but transportation constitutes a significant part of our CO2 emission portfolio, right? So we need to be very careful. This is an important area where a lot of things can be done. Just to highlight again what affects my cost, right, of CCUS. So the type, the flow rate, the composition of the source, and then when we talk about capture, what is the technology we're using, what is the material we're using, what is the composition of the CO2 in the initial gas, what is the scale or flow rate, what is the purity recovery, all these affect our cost. And then in a transportation, the distance between your source and the sink is important. Your transportation mode, whether you are transporting CO2 in the liquid form or in a pipeline, or using offshore transportation, marine transportation versus onshore. So all these have different cost functions. And then where you're utilizing, is there a market for CO2? Can I sell it? Or if there is a carbon tax, or can I claim credit? So all these will affect your CCUS design. Again, if you go for cost-based design. A sequestration part, what is the type of storage? Is it saline formation, or is it an enhanced oil recovery, or is it a natural gas, depleted natural gas reservoir? So all these have different cost functions. So altogether, if you summarize what is going on in this CCUS domain, so it's a multi-scale problem, right? You have different pathways, different processes, and supply chain and policies, and there are different questions, challenges there in terms of which technology we should use, what will be their cost, how we distribute these technologies across different sectors, and what scale we should implement. So there are a lot of multi-scale activities in design, in control are happening in the process systems area. So recently we summarized many of these areas, challenges and opportunities in a paper published last year on carbon capture, utilization, and storage, but the idea is again coming from the process systems perspective. Okay, I will just give an example on the multi-scale side of it, that how we address this question. Again, to summarize, why it is multi-scale is that you have a question of screening the optimal material, given a database of different materials of zeolites, metal organic frameworks, or solvents, or membranes. It could be polymeric, it could be inorganic. There are thousands of different choices that you can make. Then you need to design the process, optimize it. As I mentioned earlier, that optimization is very important piece. If you have a lousy process operating at lousy conditions, your cost will be very different, very high. You might not even get the required purity and recovery that you are looking for. Then you need to select which pathway I'm going to go. Should I go absorption or adsorption or membrane? Then there is a question of depending, can I have hybrid approaches on material and processes? And then all this together contribute to the design of the supply chain. So these are the material, process, technology, and supply chain scales that we need to be cognizant about. I'm just going to give an example of what we did in this in this domain of multi-scale optimization of carbon capture and storage. So as an example, we picked zeolite as material. This is, as I mentioned earlier, is a microporous materials. Here I'm showing a microporous structure of a modern zeolite. It is crystalline aluminum silicate materials with very high surface area. So, and it selectively absorbs carbon dioxide, and nitrogen is not absorbed much. So it is a great material for, or a class of materials for CO2 capture. But if you look into these materials, there are many materials, like more than 250 zeolites are existing, either synthesized in the lab or naturally occurring, but there are millions, literally millions of different structures which are hypothetical, which are not discovered yet, but we can consider them as potential candidate for CO2 capture. So what we did, we started with this database of crystalline hypothetical structure of many different zeolites. You can characterize them based on their portal, channels, and cages at a atomistic or microporous level. And then you can develop models, simplified models of these zeolite structures. You can also perform a different selectivity on those atomistic structures. For example, one is shape selectivity. Just to give an example, let's say if we have a zeolite LTA, which has at the atomistic level 8-ring portal, where it's kind of a gate to the pore that this zeolite have. And then if you want to push different gases, depending on the energy differences and the energy barrier that these gases these guest gases will face when it tries to enter the pores, you will have different selectivity. For example, if you CO2 can have free passage to this LTA, versus if you want to push methane, it will have a different energy. So based on this, you can create shape selectivity. You can also do molecular simulation on different structures, that how much CO2 can be absorbed given a zeolite configuration. You can do multicolor simulation on those, and it will give you equilibrium absorption of CO2 and nitrogen. Based on that, you can create a selectivity criteria where you can say, okay, I know at a given pressure and temperature, this much of CO2 is absorbed versus this small amount of nitrogen is absorbed. So the difference or the ratio of CO2 and nitrogen absorption will give you an absorption selectivity. So at the molecular level, you can play with these shape selectivity, absorption selectivity, like this, and size selectivity, and other material-centric metric. Using those, you can create a preliminary list of zeolites that are potential candidate for carbon capture. Here I am just showing an example of that. And with those kind of study, we was very effective, because at the end we could actually find multiple new zeolite, and I'm showing some of the structures here, and their corresponding cost of capture when we put them in our process. And it shows a very cost-effective way of capturing CO2 if you use AHT or NAB. These are new type of zeolite frameworks which previously people did not think about. So that kind of gives us some confidence that, okay, there exist new materials which can reduce the cost of CO2 capture. And we put all this together in a computational screening framework, where you start with a database. Either it could be zeolites or metal organic frameworks, or other porous materials. You do the shape selectivity, size selectivity, and absorption selectivity based pre-screening, and then you just take the most promising candidates and do the process optimization that I talked about earlier on PSA process. Based on that, you can ultimately come up with a rank ordered list of materials and processes that are most cost effective for carbon capture. So some of the results that I'm showing here, we did this, we applied this framework, and we came up with many materials actually in zeolites, which shows promising separation of CO2. So here I'm again showing the cost of capture and compression for different zeolite materials. Each of these represents a zeolite, and in the horizontal axis, I'm showing their relative absorption selectivity in the logarithmic scale. And you can see that the cost is about 25 to $40 of many of these materials. I'm also showing some of the energy penalty that these materials have. A significant amount of energy needs to be put to capture CO2, even if you use this kind of materials. Okay, then we thought that's great. We can screen materials and we can calculate the cost at the process level. But if somebody wants to develop simple models, I want to make decisions based on all these framework, it is not easy. So what we suggested at the end, that let's develop simple input-output model based on this entire framework, where you can, if you give me the composition of the CO2 in the flue gas and the scale or the flow rate, F and X values, then I can compute the investment cost, given that this alpha, beta, N, and gamma, and M, these are estimated based on the computational data that we generated in our lab. So using different flow rates and compositions, we generate input-output data, feed that data in this kind of simpler input-output model, and use that model for supply chain optimization, because that allows us to handle the complexity at the level where we want to answer questions, let's say at the supply chain of CO at the US or a statewide or region-wide cases. So this simpler model is kind of the bridging model between our material and process with the supply chain. If you plot that, use that model, that's how we can generate this kind of decision-making plot, where somebody can say, okay, I have a source with a flue gas composition of 10%. What is the best technology? What is the best material? So you just come to this plot and you can look into this. And for example, in this, if your composition is 10%, the best technology would be pressure swing adsorption based on MBY zeolite, which has a cost about $40. So this is how we can use this plot. And we can use this simple model in the supply chain as well. So this can be found in a paper that is published in 2015 from our group. Now, as I mentioned quickly, that at the supply chain level, we can use the simpler cost functions, and that's what exactly we did. So we considered this source data, composition, their flow rate, their locations, the sink data, their estimated amount of CO2 that can be sequestered, utilized, all these, and then the simple models coming from the process like absorption, PSA, or membrane, and the materials like MEA, zeolites, all these. So these simple models comes into a big supply chain model, and then we kind of integrate these all together. At the end, we are able to make it a mixed into a linear type of programming model, which we were able to solve. And the solution was very interesting. If you look into some of the solutions, like, okay, what is the best network that you can generate for CO2 management, for if you want to reduce the emission in the United States by 50%. So here we see that not all sources needs to be picked. So you can just selectively pick the sources and selectively pick the sinks, and you can connect the new pipelines between them. But the question, if you don't do optimization, then this kind of network design is not easy. So here we have a systematic framework that can be used to do the same for us. We can also answer the question, okay, for a 50% reduction or any different levels of reduction what will be the investment, how much in cost that you need to put for capture, how much cost you need to put for pipeline, and so on and so forth. What will be the overall cost of your network for every ton of CO2 that you are capturing, which material you should pick, and which sources you should pick. There are some interesting results we got. For example, if we analyze this plot, which is again a busy plot, but let me summarize for you. It shows the cost of different selected sources. And as you can see that their cost for different sources are different. So depending on the size, the scale, and the composition of these sources, I have different dollar per ton value. If you look into the transportation cost, for example, here, again, it's not just a fixed dollar per ton value. If the source and sinks are located far away, their costs are higher. If they're located close by, then their costs are low, but you may not get always nearby sinks. So you have to do a trade-off between the location and the scale and the capture technology selection. All right. So the idea here is that we have a framework. The numbers are not that important, but because that those changes in turn based on your own specific problem, but the framework that remains. So you can apply that for different problems, different locations. Here I'm showing results for a statewide CO2 supply chain network design for Texas. And again, the idea is that you are given different sources of CO2 and potential locations for utilization and storage, and you optimize that and generate a network like this. Interestingly, the optimal network has two distinct regions. So the supply chain, if you just consider based on Texas as a state alone, and if you don't consider overall nationwide capture in your model, then this design is different than the nationwide design that we previously got. So that's another insight that we need to think, that we need to consider systems level design rather than just focus on our local CO2 management. Okay, so last piece that I want to bring in before I conclude is that there are new considerations that we need to consider when we want to design carbon capture and supply chain models. One of them is carbon pricing, because this is a potential way of implementing or forcing or asking or suggesting industry to invest in carbon capture. If you don't do carbon capture, if the carbon price is there, then you might need to pay this price or penalty. So the question is, for a given carbon price, what level of capture should we do? And that's not an easy question to answer. So here I'm just showing that there exist indeed different locations across the world that carbon price that are implemented and imposed. So we're moving towards a world where not only just we're capturing just because of sustainability, but also there are penalty that we might need to pay if we don't do that CO2 reduction. So carbon tax is one of the mechanisms. The other mechanism is cap and trade. That is something implemented in California, for example. The idea here is that rather than imposing a tax, you can say that, okay, you're going to have different level of regulations for different years of CO2 management. You need to capture this amount of CO2 next year, and then you need to capture more in the next year, and so on and so forth. So there will be a staggered or stepwise reduction in this format of cap and trade. So if you want to operate your business, for example, in the cap and trade domain, then we need to think about a multi-period supply chain design rather than one fixed design, because you have different amount of caps of CO2 that you can emit. So that's very important consideration that needs to be done in the supply chain also. So to summarize, like overall, a market-based approach can be imposed there. So these are new considerations that needs to be that needs to be thought. Let me just quickly move on to some of the other issues that we are currently working on in terms of CO2 management. Another very interesting issue is that once you have a capture technology, how do you integrate that capture technology in your own system? Here I'm showing an integration problem for a coal-fired power plant, which also integrates carbon capture in it, but because carbon capture is very energy intensive, it needs to either reduce its production overall supply to the electricity grid, or you need to tap into other renewable sources. But interestingly, what we found is that carbon capture processes can be flexible in a manner that it can act as a pseudo energy storage. For example, if you can decouple the absorption and desorption at a different time, then actually you can use these as a battery for storing the solvent. And instead of using a battery for storing energy or electron, here you're storing solvent that needs to be regenerated. When you have surplus renewable, you can use that excess renewable energy to regenerate your solvent at a different time. So this kind of leads to a very interesting design and scheduling optimization problem when you want to do flexible carbon capture, which can help make a portfolio which is more optimal in terms of in the presence of different electricity price at different times, given the day-ahead market. So these are very interesting questions that are coming from the power plant perspective, that how do we use the flexibility in capture to reduce some of the intermittency challenge or the variability challenge that we see in renewables. Some other questions that I want to just highlight that we're also working on is, as I mentioned, the synergistic integration or systems integration, and the design and scheduling optimization. There are multi-scale optimization problems and life cycle sustainability analysis that we need to consider. We do not want to emit more CO2 when we rather than capturing CO2, right? So we need to be very cognizant about the amount of CO2 that is avoided rather than just focusing on the capture. There are a lot of opportunities for hybrid modeling platforms, machine learning. I did not talk about those because of material screening, process optimization, and supply chain design aspects of CCUS. And I did not talk about that at all, but it is getting more and more important as we think about uncertainty. When we design a process, we do not know what will be the future economics, the price of electricity, what will be the process parameters that we should use. We do not know how much CO2 we can actually retain underground. So there are a lot of uncertainty in the storage capacity. So all these needs to be handled in a robust way, either using stochastic optimization or robust optimization frameworks. Okay, so with that, let me conclude here. So I wanted to highlight in the space of CO2 capture is that the cost is very important, and it is very important to have an apples-to-apples comparison between different technologies. If you want to do cost calculations, it is not an easy task. So you need to implement multi-scale frameworks to do that. Scale and compositions of your initial flue gas play a significant role. So we need to be very careful about that when we calculate the cost. And we found that no single technology like just MEA is not enough, or just membrane is not enough, or just adsorption is not enough to address different scenarios of CO2 capture. Depending on your source, it could change. So multi-scale systems engineering plays a significant role in selecting the materials, processes, and networks that can be optimal. The unresolved questions, as I mentioned, is that feasibility is one of the other aspects that I really did not touch upon, but it is getting more and more importance, especially in the case of direct air capture, capturing CO2 from air, which is most challenging problem. So we need to be careful about how we design, what will be the cost, what is the energy implications, what is the environmental justice and other issues, not only just for direct air, but any other capture processes that we think about. Systems integration will play a key role when we try to integrate capture in different sectors. Okay, so with that, I would like to stop. And again, thank you for your time, and I'd be happy to answer questions.
That was excellent, Faruque. Let's virtually thank our speaker, please.